So up to now, we have covered the techniques at the top. Well, not completely, right? We've looked at one-dimensional proton and C13 NMR. We talked briefly about infrared and UV visible spectroscopy. And so now we're going to talk about mass spectrometry, and this will take a couple of weeks. So this goes a little bit, well, I think the amount of time we spend hopefully, is correlated to how much information we can gain from the technique, right, and how applicable it is. So I think, mass spectrometry is a pretty good, useful technique. So today we're going to talk a little bit about some instrumentation, ion formation, and talk some about the molecular ion. So we're going to spend most of our time talking about an ionization technique called electron impact. And this may not be the one.
Is there an acronym for that?
EI.
Yeah.
Usually like this, I think. May not be the one that you use most often, but this is the technique that we can really get more information about fragmentation and these kind of mechanisms. So we're going to go through and talk mostly about mass spectrometry based upon this ionization technique, and then we'll come back and we'll talk a little bit about some other ionization techniques and some, just different mass spectrometry methods. Okay? All right, so what do we get from mass spectrometry? Right, so kind of follows the name. We get something about mass, right? But what exactly do we get about mass? Do we measure just the mass directly?
Mass to charge.
Right, it's the mass to charge ratio. Usually we call this M over Z equals mass to charge. Most of what we'll talk about gives us a charge of 1. So we get the mass from that. But there are techniques that we'll talk about later which are mostly applicable to big molecules and proteins and things like this, where you can have a multiply charged ion. Okay, and there's some advantages to that if you have very big molecules. All right? So we measure the mass to charge ratio. Hopefully from that we can get some information about the molecular formula, right, ideally. And then once we have generated this, we oftentimes get some information about connectivity of atoms based upon how the molecules break apart in the mass spectrum. All right, so in order to get this information, instrumentally there are kind of 3 different stages that have to take place. Okay, the first stage is that we have to be able to ionize the samples. Right? And this is the easiest if we have small molecules. Well, it's not necessarily easier to ionize, but yeah, I'll talk about that more. So we're going to, like I said, we're going to use this electron impact. And so this is going to go from our molecule, we usually call this M, to some ion. Right? And we're going to usually get a species that we're going to draw like this, and I'll talk about that more in a minute. So once this ion, and if this ion contains all of the atoms of the molecule, it's called the molecular ion. All right, that can then fragment. Okay, so we get some kind of, I think I'm supposed to do this on later too. So we're going to lose some piece here, and we're going to get an ion like this. So we're going to lose various fragments. So then after we do this, we have a mixture of ions we have to be able to separate those ions, and then we have to be able to detect them. Okay, so these are kind of the processes. So here's an example of one type of mass spectrometer. This is a kind of a single sector instrument. It means we're going to separate the ions one time. All right, and so in this diagram we have several pieces here. We have, this is the sample chamber, or what they call the ion, no, that's the other part. This is the sample inlet. So we need to have a way to introduce our sample into the mass spectrometer. In electron impact, this whole system is under high vacuum. All right, so what we do is we have to volatilize the sample, so it has to evaporate, it's under vacuum, and it goes into what's called the ion chamber. Okay, and so they're neutral at this point. So they just kind of float into this chamber because it's all under vacuum, and then we have this filament where a voltage is placed across here, and it essentially shoots electrons across this gap. And so when that happens, our molecule gets shot by electrons. Essentially, it gets excited, and then it ejects an electron. And so we draw it like this, plus an electron. So this is excess electrons here. All right, and this is a radical cation. All right, so once we've generated the cation, so it's gotten hit by the electrons here in the middle, once it's charged, we can manipulate how it, what it does, essentially. So on the left side over here, they have a positively charged plate. It's called the repeller plate. So if we generate a cation here, we have a positive charge over here. It's going to be driven away. It's going to be repulsed by that, and it's going to be drawn away. On the other side, we have these negatively charged accelerating and focusing plates. And so they have to be able to, I think, kind of go on and off. So they attract the cation and accelerate the cation in this direction, and then I think they have to be turned off and back on so the cations don't just stick to those plates. Okay? So the ions get accelerated down this tube. Okay, so they go like down this tube. And then they go through this magnet, and the trajectory is bent by the magnetic field. All right, and the amount of curvature here, how much, so if we have this is a curve here, part of a circle, there would be a radius for this curvature, and the radius of that curve equals the square root of the mass to charge ratio times 2v over b squared. Okay, so the mass to charge ratio we talked about. V, this is the voltage at the accelerator plates. Okay, acceleration. And B0, like in NMR, is the magnetic field. All right, so for a given mass to charge ratio, here we could turn that equation around too. Let's do this. M over Z equals B squared R squared over 2V. So for a given mass to charge ratio, it will only have the right curvature to go through this exit slit to the collector when it has the correct combination of magnetic field and voltage, accelerator voltage. Okay? So essentially what we can do is we create a bunch of different ions, molecular ions, and then they fragment, and we get these fragment ions. They all get accelerated down the tube, and then what we have to do is scan through usually the magnetic field. And this whole thing is going to kind of, see, they have different ions shown in this drawing. Some are going off to the side and are not measured, but as we scan through the voltage, essentially this beam kind of bends over, and some combination of those, each ion will go through the exit slit and be measured. All right, and so we can see from this, because the radius of the arc is proportional to the square root of the mass to charge ratio, right? A higher mass to charge ratio will have a wider turn, essentially. So the one over here would be a higher mass to charge. The one that's curving more would be a lower mass to charge. And so we just have to vary the magnetic field, or we could vary the voltage at the accelerator place, so essentially vary the speed at which the ions are going down this tube to go through and be able to measure all of those ions. Okay? So once they go through that slit, then they're detected and they give us, some kind of a printout. All right, is that?
So for the connector, it cannot connect the lower or the much higher mass to charge ratio.
So at one value of V and B, only one mass to charge ratio will go through here.
Okay.
But if we change what B is, that at different values of B, each of the different ions will go through the exit slit and be measured. Okay?
Okay.
So that's the general idea. So the ionization, so this is just a blow up of this, this ion chamber. Okay, so in EI ionization, the sample's volatilized, like I mentioned. The molecules go into this vacuum chamber. In fact, what you have to have is this method to usually put the sample in a little tiny glass tip, and it goes on to the tip of a probe, and the probe goes inside, and it has to be sealed against the vacuum. And so once you put it in the vacuum chamber, you can heat it if you need to get it to volatilize, and then you have the vapor in the ion chamber. They're bombarded by the electron beam. They generate these radical cations, and then those energized ions can fragment. Okay, so I kind of already mentioned all of this. Okay. All right, so the first thing we're going to look at here is the molecular ion. So, that's the most important ion that we can observe, really. And so we need to be able to identify whether an ion that we observe is the molecular ion or not. There are situations where if molecules readily fragment, they'll fragment so much that there won't be a molecular ion observed. All right, and we need to be able to know that. So there's several criteria for molecular ions. One is that it has to be the highest mass ion in the spectrum. Okay, because if it has all of the atoms, then it has to be the highest one. Not worrying about isotopes and things like that at this point. Second thing that we'll talk more about is that it must be what we call an odd electron ion. Okay, so remember what we did is we started with this M, and I'll just say draw a pair of electrons here because stable organic molecules are going to have complete octets and things like this. We shoot this with an electron, and we're going to lose one of those electrons. So let's say, draw it like this, plus an electron. So we started out with that pair. The plus we're drawing here is kind of a vacant spot. You know, this electron came out of that spot, right? So what we generate is this radical cation that now has an odd number of electrons. Right? Yeah.
Can we do it the other way where we get a negative M with an extra electron?
There are methods to look at negative ions.
Okay.
Yeah.
Usually they'll do that. So if they like if you send mass spec samples off, if they don't have the exact mass that you predicted, the positive ion spectra. And
They'll use different techniques. Yeah.
Or just do.
So you'd have to. What would you have to do to look at anions? You'd have to change the.
Flip the plates.
Right. You have to flip those plates. Right, because you want to accelerate. Right now, we are accelerating the cations. Right? The anions and are either going to be drawn the other way to the repeller plates. Anything that's neutral is just going to be sucked out in the vacuum. Right? So out of all the species that are being generated, so far all we're observing are the cations. Okay? Anything neutral, we don't see. All right, and so this is called an odd electron ion because it has an odd number of electrons. Okay, and the third thing, which is hard sometimes because we really can't, or we can't, I can't at least, really show how all of the ions are formed. All right, but we must be able to, the molecular ion must be able to yield all other important ions by logical losses. Okay, what that means is that fragmentation should follow, reaction mechanisms just like any other reactions we talk about. Challenge here is that we really have very high energy ions, and so they can do a lot of things beyond what we're going to talk about, right? But hopefully we can focus on what we would call the important ions. All right, so we generate these ions, okay, and how are they generated? All right, so some examples. So if we have something like an ether, Right? It has 2 pairs of non-bonding electrons. We shoot this with electrons, and we most easily lose one of the non-bonding electrons. Okay. If we have a pi bond, we can also lose pi electrons. So we could draw this like this. Okay. We can also we can lose electrons just from sigma bonds as well, but this is a higher energy process. So if we just have some sigma bond between 2 alkyl groups, we can just generate like this. Notice that in this case, all of these, we'll draw it like this, are odd electron ions. Okay? The common ionization points are usually the non-bonding, are the most readily ionized. They take the least amount of energy. Then we have pi electrons followed by sigma electrons, or bonds, electrons in sigma bonds. All right. When a molecule fragments, I'll just draw this here. When we lose a fragment, what we generally yield is a fragment ion that's an even electron ion. Okay? Here, let me redraw that. I'm going to draw it like this. What we're going to lose usually is some radical. Okay, so the radical goes to a neutral piece, which we don't observe. We end up with an even electron ion now, which is our fragment ion. Okay, we'll look at this in more detail.
So we observe the even, not the odd now?
We observe all of the cations, but most often, and we'll see some exceptions to this, most often the fragment ions are even electron ions. Okay? And that really depends on the fragmentation mechanism. If we're cleaving just one bond into 2 pieces, then we get even electron ions. If the cleavage involves some type of rearrangement, then we'll get a fragment ion that's an odd electron ion, and that will be something that we can identify and will mean something to us when we see that.
But the radical we won't see.
We'll never see the radical because it's neutral,
Okay.
right? So there's no mass spectrometry method to directly observe the radicals. All right? Our calculations for sites of unsaturation work for odd electron ions. And if we see an ion and we figure out even the molecular formula of an even electron ion, we'll end up with an unsaturation number that's to a half value, like 5.5 or something like that. And if we did that, that would tell us that that has to be a fragment ion as well. All right, so what about the mass of this molecular ion? So for most elements, there's a relationship between the most abundant isotope and the valence number. Okay, so they're either both odd, So it could be, protons has an odd isotope and a single valence, right? It forms one bond. Or it could be something like chlorine, has chlorine 35 and it has a single valence, right? So they can or they could be both even, right? So this could be something like oxygen makes two bonds, has a isotope of oxygen 16, right? We have carbon, same thing, right? For these situations, when we have an odd electron ion, they will have an even mass. Okay, so let's just pick out a few examples. If we just take a very simple one, methane, right? It has elements that all fit into this. Massive charge of the molecular ion would be 16. It's an even mass. If we have something like C6H5OH, this could be phenol. Right? We add that all up, mass to charge equals 94. Okay? So usually for all of the elements that fit this pattern, we will always get an even mass for an odd electron ion, or the molecular ion. Nitrogen is the exception to this, okay, because nitrogen has, a valence of 3, and it has an even mass of 14, okay? And so if we have a nitrogen, if we have something like ammonia, right, we have 14 plus 3, mass to charge equals 17. If we have something like ethylamine, all right, we end up with a mass to charge of 45. So if we have one nitrogen, we'll have an odd mass for the odd electron ion. However, what if we have two nitrogens? So let's put it up here. I'm just going to write a simple one like hydrazine. We have two nitrogens now. So we have 14, 15, 16 times 2. Mass to charge would equal to 32. All right? So this leads us to what's called the nitrogen. All right? And this says is that an odd electron ion, okay, molecular ion included, will have an even mass if it contains an even number of nitrogens. 0 included. 0, 2, 4, 6, on up. All right, the odd electron ions will have an even mass. And then the converse is true. If there's an odd number of nitrogens, the odd electron ion will have an odd mass. Okay? The even electron ions, which are generated through fragmentation, are just going to be opposite. Okay? So an even electron ion containing, well, this always turns into a complicated thing. Let's say here, okay, so I said an even electron ion containing an even number of nitrogens will have an odd mass. So we could have a whole bunch of different variations of this. So let's kind of draw out what would be happening. Okay, so if we have no nitrogen, okay, so 0 nitrogens, we're going to generate our molecular ion is an odd electron ion. Okay, and this will have an even mass. If this fragments, then we will get an even electron ion, and this even electron will have an odd mass, and it will give off a neutral piece. Okay, the radical usually. Okay? So this is the most common situation that we'll see, right? But if we add a nitrogen, so let's say we have 1 nitrogen, then our odd electron ion will have an odd mass. Okay? If it fragments in the same way as up above, then the even electron ion should have an even mass. Okay? This is true as long as this even electron ion still includes the nitrogen. Right? Still 1 nitrogen. However, it gets more complicated in this case because what if when it fragments, the neutral species that comes off contains the nitrogen? Right? Then what would we get? Right, then we would get an odd mass.
That is if we split 2 nitrogens. So you go from even to odd, so it'd still be even.
Right, so yeah, if we had a molecule with 2 nitrogens, it would be even. And if it fragmented with 1 nitrogen on each piece, then we'd have 1 nitrogen in our fragment ion. We'd have an even mass. Right, so you can go through a whole bunch of perturbations here. So if the fragment, let's see, it includes the nitrogen here, right, then we're going to have, we'll still get an even electron ion from our fragment, but this would have an odd mass. So this would have no nitrogen in it.
So if you start off with a nitrogen, you have an odd mass, or 1 nitrogen, or an odd nitrogen amount. And you fragment the nitrogen, you still have an odd mass.
If it fragments and the radical that's lost takes away the nitrogen,
Right.
then the fragment ion, the ion that we observe, would have an odd mass. Right? Because then essentially what we've done is gone from down here to up to here. Right? Because this one has no nitrogen in it.
And you could do the same thing too if you had 3 nitrogens.
Yeah, sure.
You lost 1 of them but kept 2 of them, then you would have an even mass.
Right.
So you would have an odd.
You'd have a whole bunch of different, possibilities here. So whether the mass of the ion, either the odd electron ion or the even electron ion, is odd or even depends upon how many nitrogens are in it. Okay? So the next thing here, so these are for the molecular ion that we said, is that the fragment ions need to be able to be generated by logical losses. Okay, so it's going to fragment, and the loss can't just be any mass, right? It has to be made up of atoms, and atoms only come in certain masses. So here's a list, it's probably kind of small back there. Here's a list of low mass neutral losses that are possible. Huh?
See, I can see it better on the board than I can.
Oh, really? Yeah. So notice, you know, certainly we could lose a hydrogen atom, right? That makes sense. Maybe we could even lose 2, but notice there's a big gap between, you know, we're not going to lose 5 hydrogens all in one shot, right? So there's no logical loss of 5, right? So there's a gap that goes from 2, essentially, up to 15.
So if we had a molecular MZ rate, MZ number of 100, and we saw another fragment at 85, we could assume that we lost the CH3 group.
Yeah, that would be a good assumption.
Okay.
But if we we saw another major ion that was a loss of, looked like a loss of 5.
Confusion.
Well, that would suggest that the highest ion we're seeing is not actually the molecular ion. Right? Because you can't lose 5, so there must be a molecular ion that's higher that could fragment to this one and to the other one.
Okay.
Okay? Because that just doesn't fit into a logical loss. And so if we see ions that cannot be generated by a logical loss, it means that our starting point, our molecular ion, is probably not right. Or we have a mixture of compounds or something like that, right? An impure sample or something like that. So uncommon ones are things like between 3 and 14. Those are not logical losses. If we go on up, we see 15 we could lose, 16 are some combinations here, 17 is an OH, 18 is water, you can sometimes get dehydration type of reactions, 19 is fluorine, 20 is HF, but there's a gap right here again, 21 to 25 are uncommon losses. Okay, so there's just not easy ways to lose those masses. So we should see losses that are common, or logical at least. All right? It has to do with the abundance of the molecular ion. So really what we're measuring when we look at the ions, we're just kind of measuring their concentration or their abundance. The most readily formed ions are going to be bigger, right? They're essentially just counting the number of ions. All right, so the ion abundance depends upon its stability and the amount of energy it has. In general, the stability of the molecular ion parallels its chemical stability. All right, so the most abundant are usually ions that are, say, aromatic. Right? Because there's not, super easy ways to just break the aromatic ring apart. All right? The next might be conjugated systems. Right? Or conjugated alkenes, or even cyclic compounds. Because then you have to break more than one bond, again, to break it into separate fragments. And so there are, I don't know if I'll have to look through the tables in our book. I've got this other book that's, well, what I learned this stuff from, which is, some of this hasn't changed in quite a while. But it gives some tables on different ions and what their abundances would be and things like that. All right, so what does a mass spectrum look like then? Okay, so here's just a mass spectrum of, I think this is what, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, C12, dodecane. All right, so The molecular ion is out here at 170. And what do we observe? So this is an even mass, right? What about all the fragment ions that are at least labeled?
Odd.
They're all odd, right? So these are all even electron ions, and they're all odd masses. All right, so we talked about if you change the number of nitrogens during the fragmentation process, right? But of course, you can never start with no nitrogens and add a nitrogen in the fragmentation, right? So what else? What kind of pattern do you see?
29. 29.
Well, we see 29, right?
43 is the largest peak.
Yep, 43, the largest peak or the most abundant.
41. So it's 3 carbon. Well, CH2, CH3, CH2, CH2.
Yeah, we call this the base peak. Okay, the base peak is always set at 100%. Okay, so they just adjust it to put that one at 100%. Okay, what else though about like a pattern or something?
Get chopped in half. You don't see anything above 85.
Right, yeah,
Fragmenting.
right,
It's not stable.
right. So we mostly are seeing low masses.
It's weird that the line pattern isn't the same for all of them. Like 43, it goes 43, a really small one and a tall one, but 57 has a really tall one and 2 even.
Yeah, so this just means that, you know, there's another ion, a separate ion that's forming there and here, and so there are always going to be some that we can't.
Don't they usually have like a finger?
Isotope.
Yeah, yeah, we'll get to that. So the point that I'm trying to get to is what's the pattern here?
You're losing 15. Or, well, 14.
14, right? 14, 14, 14. So we're just cleaving at different points along this chain, and it just is a difference of a CH2 group, right? So for a linear alkane, we're going to see a common pattern like this. And so most of these ions are formed, right, from the molecular ion fragments to give 2 pieces. One is a radical, one is an even electron ion with a mass of 84. It doesn't go to there usually and then lose another 14 and then lose another 14. This would go from there to here, from here to here, like this. All right? And so essentially what we're doing is we're cleaving at different points along this, right? So 43 would be cleaving here, right? And the charge would be going on this side. That's a 3. So essentially, like I mentioned before, we would have something like this. Let's just draw this bond with 2 electrons in it. However, I'm not going to count those. All right, and so then we ionize. I didn't really do that quite right. Well, we'll get the idea. And we lose an electron here in that bond. And then this bond is essentially weakened, right? And so it breaks. Radical goes to one side, cation goes to the other side. We end up with a cation like this, plus a radical that's like that. 3 carbons. This is the mass to charge of 43. Okay, cleave at either end, right? charge goes to the smaller piece. And in general, what we see most often is the loss of the larger radical, the larger mass radical. So if it ionizes at that bond, then we lose the large mass radical and get the smaller cation. Right, so that one would be 43. If we cleave one higher here, that would give us 57. Cleave here would give us 71. You know, cleave here would give us 85. And then we're essentially to half, right? So if it cleaves anywhere on the molecule and it loses the larger mass radical, then we get this series of ions. I'm not exactly sure why. I guess I should try to look this up too, but why 43 tends to be the molecular ion for, you know, these kind of linear alkanes. Or not the molecular ion, the base peak.
Probably because less carbon, so it's probably easier on both sides, and then you can move the positive charge.
Yeah.
Same thing with 57, but
Yeah, you can do the 57 is almost the same. So in general, what we want to look at though is we mostly want to look at the biggest ions. So ideally, we could explain the formation of the base peak, and we're going to generally look at the higher mass ions, right? Because an ion, for example, like 29, what would make up 29? An ethyl group, right? Lots of molecules could have a little ethyl group, right? And so that's not as diagnostic for us as a higher mass ion, where we've lost an ethyl group would tell us more than showing an ethyl ion. Okay? If we have a branched chain alkane, we see that the pattern of peaks is not as regular, right? And first off, we don't even see this time a molecular ion. All right, just because it's fragmenting very easily. And because the ion abundance is related to the ion stability, right? If we can generate a tertiary carbocation, that's going to be more stable than a primary carbocation, right? So 57, the base peak can get formed by cleaving this bond, and we get, you know, this tertiary carbocation, which is the most stable one. And it can happen on either end, and we're losing a large mass.
Would it happen at either end at the same time? Like, would one molecule split?
No.
It doesn't get cleaved into two chunks?
No, usually we're going to see, well, usually these reactions are, we just call them, you know, unimolecular reactions. We're in a vacuum, so we don't see an EI, you know, bimolecular reactions between molecules. And usually we won't see remote ionization and cleavage.
Or two electrons could just cleave it at both tertiary.
you form two radicals then.
Well, we'd have to form two cations, right? And I think that that's a very improbable process.
It is? Okay.
Yeah.
So I have to happen at the exact same time, because as soon as like.
Yeah, you'd have to get hit by two electrons and ionize twice, and yeah.
It's gone.
All right, so the next thing has to do with what you guys were talking about already, is that, and this isn't really the best spectrum to look at for it, but notice that, you know, all of these ions have some other peaks that surround them, right? And usually what we're interested in are the ions that are just slightly at a higher mass than the big ion, and these come isotopes. All right, because we're in this method, we're separating them by unit masses. If we have an isotope that has +1, then we'll see that ion as well. So here's some common isotopes, all right, that we can observe. So carbon, right, we've already talked about carbon isotopes, right, because we know that C13 has a 1.1% abundance. Right? And that's what we were observing in C13 NMR. We can observe that in mass spectrometry as well. Okay, so for every carbon in the molecule, there's a 1.1% chance that that carbon is a C13. Okay?
And the more carbons you have, the more you would see that relative abundance increase.
Right. So essentially, if we had one carbon, and we'll play around with this later, if we had one carbon, then what we call the M+1 peak should be 1.1% of the molecular ion. If we had 5 carbons, then that M+1 peak should be 5.5% of the height of the intensity of the molecular ion. Right? So we can actually get information about the number of carbons based upon the size of that M+1 peak. All right, so there's other important ions here too. You know, deuterium is pretty small, but it can contribute N15.38. You can see that. But some of the important ones are the halogens, right? Chlorine, they set the most abundant ion to 100%. So chlorine has 2 ions, 2 mass units apart, chlorine 35 and chlorine 37, and it's roughly a 1, oh, did it the backwards way, 3-to-1 ratio. Okay. Bromine has bromine 79, bromine 81, and look at the abundance is 100 to 98. So these are roughly a 1-to-1 ratio. All right, so these two especially are really the easiest to pick out. But you know, there's some of these other ones. Silicon, if you had it, you'd have some different. You know, look at that. It has an M+1 at 5.1, M+2 at 3.35. So they would play into it. Oxygen has oxygen 18 at 0.2%. Okay, so all of these would play into the relative abundances of the cluster of peaks that we see for an ion. All right, so let's just stop there. We'll start looking at some spectra next time. All right.